All right, welcome everyone. I think we're going to kick things off. My name is Ben. I'm one of the co-presidents of the Charles River Economics Labs. We're a group of Harvard, Stanford, and Chicago undergrads that partner with government organizations, intergovernmental organizations, and nonprofits on pro bono economic research projects. And this semester, our project partners include the U.S. Census Bureau, the Massachusetts Department of Economic Research, among others. We are incredibly excited to welcome Sendhil Mullainathan today. Sendhil got his PhD in economics here at Harvard in 1998, began his academic career as an assistant professor at MIT, came back here, and then left us in 2015 for Chicago Booth, where he's currently the Roman Family University Professor of Computation and Behavioral Science. His work has covered a wide range of topics, including discrimination and poverty, behavioral economics, and most recently, the application of machine learning, which he's going to be talking about today. He is the co-author of the book Scarcity, co-founder of a number of organizations, including JPAL, Ideas 42, Nightingale, and Dandelion, and a recipient of the MacArthur Genius Grant. So Sendhil is going to talk for about 45 minutes, at which point we'll open it up to the audience for questions. So, Sendhil, the floor is yours.
Great, thanks. I'll just dive right in. I'm going to talk about two things. This is a talk that goes in two directions. You can read the title here. Let me start with the bottom direction. Is this going to have feedback? Or can you hear me without the mic? I'm going to try without the mic. Can you hear me without the mic? Here, let's do that. All right, I'm going to start with why behavioral economics needs AI. And to do this, I want to talk a little bit about something that happens in the United States a lot. Every year in the United States, about 12 million people are arrested. If you just pause and think about that number, that is an astonishingly large number for a country of 300 million people. If you ask what does the United States do well, it arrests people extremely well. Right after arrest, there's a question that has to be answered within about 24 hours of arrest, which is where will this person who's arrested wait for trial? Will they be sent home to wait for trial, or will they instead be sent to jail? This is an extremely consequential question because it has implications for society in that imagine you just arrested somebody who's committing a violent crime, a murder, or rape, and then you send them home and they do it again before trial. That's terrible. You had this person arrested. But it also has implications for the arrestee. This is not a decision, this is a decision made very quickly. This is not a guilty person, it's just an arrested person. You send them to jail, the average wait time in jail is about 2 to 3 months, in some jurisdictions as high as 9 to 12. So without ever being found guilty of anything, their lives are effectively over. You know, it's one thing to have been arrested and miss a day of work. It's another thing to go to your boss and say, sorry, I haven't been here for 2 to 3 months. So this is about as consequential as a decision as it gets. How do you make this decision? Well, the law tells us what the judge will say. The judge actually has to basically make a judgment about two things. One is, will this person flee? Are they going to reappear in court at the time they're supposed to? The second is, while they're out on trial, while they're out on bail or waiting for trial, will they commit another crime? In other words, is this person pose a flight risk or a public safety risk? That's what the judge is supposed to do. And they have to do all of this based on the information they have available at the time that they have available. Now, there are a lot of ways to look at this problem, but one way to look at this problem is that this is almost exactly a supervised learning problem. So by show of hands, how many of you here know what supervised learning is? Okay, so for those of you who don't, supervised learning is fairly simple. You have an X and you're trying to predict a Y number. The judge has an X, everything they know about the defendant. They're trying to predict a Y, risk. Weirdly, the judge is a human being implementing the supervised learning algorithms again and again and again. If that's all the judge is doing, it begs the question, given that we have algorithms that implement supervised learning problems, such as, is there a photo that's in the classic wide learning algorithm? Is there a face in this image? Why not apply it to this problem? We could take the large data we have and actually just predict and do exactly the thing the judges do. That's what we did. We basically got a defendant risk predictor. So this is data from New York State. Tons of data. Full of data. These are real data from the judges. And all we're going to do is basically use an ML algorithm to predict the exact quantity the judge is going to predict. So now, what we want to know is how well does that algorithm do relative to the judge? And so let's think about how we do that. So on the x-axis, I put release rate. So since the algorithm is a predictor, I'm going to take everybody who shows up, and I'm going to rank them based on predicted risk, according to this algorithm. Then I'm going to decide what fraction, not decide, I'm going to, based on what fraction would be released, I'm going to release the lowest risk and continue along until all of them have been released. If I do that, that gives me the crime rate at different release rates. Obviously, if I release no one, I get no crime. If I release everyone, I get the average crime rate of that population. Now we need something to compare. This is the algorithm's performance. Of course, the algorithm can't decide how many people to release. It can just tell us how to rank people. So I need to compare the algorithm to the judge. How am I going to compare the algorithm to the judge? Or more precisely, how am I going to compare the algorithm to the current state of affairs? Well, what's nice is that we have a benchmark in this figure. Because the current system, the current judge in New York, the judges in New York, they produce this. They produce a release rate, and they produce a crime rate. They release 72.7% of people, and they produce an 11.3% crime rate. Which means, without making any decision of how many people to release, we can see the algorithm strictly dominates the judge. So that you can see that, consider this for this point here. We can say, oh, you're happy releasing 73.7% of people? Great, let's release the same percentage that you're comfortable with, and let's get 24% reduction in crime from 11.2 to 8.5%. But you don't need to go in that direction. You can go in this direction. You can say, if you were so happy with the crime rate of 11.3, let's release people until we get to that crime rate. Which means we can reduce jail populations by 40%. In other words, we can close, these numbers are insane. We could close Rikers in July and accomplish the exact same activity that we are currently accomplishing. There's some subtle issues here which we can talk about, which I'm not really going to kind of go into. You can look at it in the paper. Some of the subtle issues involve things like, if we do all of this, what's going to happen to the racial composition? I think one reason that this is a subtle issue well, maybe this one, I think I'll skip this one, but I'll just tell you in words what's going to happen. What's going to happen is, first, when you reduce jail populations by 40%, guess which race groups benefit the most as a first order effect? Anyone know?
White people.
Why would white people benefit the most?
I would assume, I don't know how the data might be trained, but maybe because of how there is higher conviction of people of color, that it might be biased towards that for.
That's the thing that everybody assumes, exactly. But if I'm reducing jail populations by 40%, on average, who's in jail?
People.
Yeah. So the first order disparate impact effect of just closing Rikers in July, by a wide margin, ridiculously favors people of color.
Oh.
Because that's who's in jail. The second effect is your point. You could say, of the people that are continuing to be jailed, the remaining 60%, what happens to the composition? And in fact, it turns out if you appropriately train your algorithm, you can actually produce perfect racial parity. So you go from a system that jails disproportionately people of color to a system that has exact equal parity while still getting these benefits. This is a little known fact that when people talk about algorithms, they talk about algorithms being potentially biased. But the thing about algorithms is they're just objects. They can be easily controlled. And one of the dimensions on which they can easily be controlled is what is their racial impact. And that was one of the key instances. Yeah, go ahead.
Does this paper also include like the types of crimes? Like does the
Great. So one of the things that we have to get into, if we open the hood a little bit, and then we'll get into the application. The other subtle issues here are, look, you've dealt with crime risk as if it was a homogeneous thing. What if I cared about different crimes? Another issue is maybe I care about the kinds of people sent to jail, such as if you have a family or an employee. That plus the racial disparity are one big category of subtle issues here. And we call them permitted payoff bias, by which we mean the payoffs that society have need to be pretty carefully specified, and you can't just say it's just this made-up crime number. The second category, which I can go into in Q&A if you were interested, is there's a very basic econometric issue here. The basic econometric issue here, which you all, if you had 5 minutes, I'm sure all of you would have come to realize there is a weird fact about this original graph I made, which is I said, oh, if I release this many people, this is the crime rate I would get. How would I know what crime rate I want to get? I know the crimes committed by the people the judge released, but I don't know what crimes the people the judge jailed would have committed. So there's a counterfactual problem here. Those are the two issues. There's a counterfactual problem. We call it selective labels, by which I mean in machine learning, labels are the outcomes. Selective because we are missing labels selectively. Some people we do not have labels for. The people that the judges believe were high risk, we do not have labels for. So the selective labels problem and the limited payoff bias are the two subtle issues. You guys should dive in and ask questions. It's late in the evening, it'll be more lively if you wanted to ask me questions. I'm happy to put that in. Okay, so those are the two issues. But what I want to kind of do in the spirit of kind of streamlining the talk is that this talk was all about can algorithms improve judicial decisions, this paper, and dealing with these issues and putting this all together. I think our conclusion was, holy cow, these numbers are enormous. Like, you do not have policy problems where you are able to get gains like closed Rikers in July. At how much cost? What are we talking about here? This is not more police on the street. This is literally an algorithm that doesn't take anything to train, a one-time cost that you can amortize over anything. So the cost-benefit calculations of this thing are through the roof. But that led us to sort of the conclusion, and this has actually now been rolled out in New York City, and there's a careful evaluation of what it actually did, and it looked like when it rolled out, in fact, drastically reduced jail populations. But you can look at that. That's a causal estimate of the algorithm. But once you realize this, you say, wow, these are dollar bills on the table. Why are we focusing on judicial decision making? Can algorithms improve decision making or policy decision making? So let's take apart the characteristics of this problem. The key feature of it is a kind of policy problem where the decision that's being made, that's crucial in people's lives, depends on some prediction. Remember how I said the judge is acting as a supervising learner? That's it. Now what's hard about the world is that you're used to seeing one kind of problem. So seeing this kind of problem takes a little bit of mental rejiggering. They're everywhere, but it takes some effort. So I'm just going to show you a few, okay? So, the police get a call. There's a domestic disturbance. Somebody's calling it in. The neighbors next door are having a big, loud screaming match. Stuff has been thrown. The cops show up at the door. They knock on the door. They have some conversation. And now the cop has a decision to make. Here's the decision the cop has to make. Is this just a couple being a couple? Or is this a prelude, or are we in the midst of some domestic violence situation? It's a very hard decision. Here's why it's a hard decision to make. As any of you who've been in a relationship know, every couple fights. So there are a lot of domestic disturbances, which are just people being people. But what you may not know is if you look at any serious domestic violence outcome, say somebody was seriously harmed, mainly women, seriously harmed in a domestic violence situation, possibly killed. Take any one of those. Look back in time, and you will find there was usually, almost always, a call to that location. A couple of months, a month before. So what that means is, we had a chance to intervene, do something. But for the cop, it's a nearly impossible prediction problem. Which of these situations do we think has the seeds of something really important? And they are authorized, in fact, just like the judge, they must intervene. That usually involves sending a social worker, that involves sometimes extreme things, like talking to the woman independent of the man, but these all are extreme actions and the cop just doesn't know what to say. That's a prediction problem. Domestic violence has many such prediction problems. Here's another one. You're all too young for this, but if you're deciding, should I buy a house? Okay, I will. How much house can I afford? How much rent can I afford? The world of financial financial advice is all a prediction problem. Given everything I know about you, what is the size of house that I predict you can afford while not actually defaulting on the house or not having a financial problem? I'm unemployed. The world of job search and unemployment is all prediction problems. How long will I be unemployed for? In which sector will I be able to get a job? If you take something as simple as unemployment insurance, which is the same everywhere in the United States, isn't it funny that we have the same unemployment insurance for everybody? We have all the data we need to predict what someone's length of unemployment spell is going to be. How does it make sense to give the same length of unemployment insurance for all these different people? Even though we can see with the data we have, some people are going to be unemployed much longer than other people. So job search advice is another version of this. Where should you search? Unemployed. Here's another one that I really like. There's an enormously large literature about education, such as the value of an extra teacher. And in this literature, we do careful causal estimates of what's the right student-teacher ratio. But which teacher? Who makes a good teacher? How do we go about picking from all the candidates who to hire? Again, that's a pure prediction problem. So once you start looking for these things, there's an endless supply of prediction problems. I'll tell you one that comes close to you in your lives. You probably don't appreciate how important this problem is. Because for most of you, this is not such an important problem. But I want you to picture that you're not a student at Harvard, but that you're a student at a community college. And no one in your family's ever gone to college before. You're going to college, you show up on the first day, and you're probably working while you're in college, so it's actually very, very expensive. Not dollar-wise, but mentally expensive. Every class you take is actually quite costly. On the other hand, it really matters. If you look at the pathways to economic opportunity, community college is the best pathway. Is one of the pathways that has been shown to be very effective. Now you show up on the first day and you have to make a decision. It's an important decision. What math class will you take? Do you take a more advanced math class? Do you take a remedial math class? Do you take an introductory math class? You guys are probably thinking, who cares? Well, for this person, it makes all the difference. If you take a class that's too hard for you and you do badly at that class, screwed. You probably will just drop out. That's the end of the community college career. You're not just disheartened, you've now lost the credit. Like one semester, you take 2 classes a semester, basically that's what you report. You take a class that's too easy for you, now you've lost that semester. So what do we offer this person? Well, there's a guidance counselor on the 4th floor of the building who's making a prediction based on your school transcript. What will be your score in this math class? What a crazy way to do it, given all the schools. And so it's striking to me that we have this problem. And the way I often describe this is I often say the same student, when they go home that evening, deciding on this very important problem, and they're deciding what movie to watch, has the world's best data scientists helping them decide what are the odds you will like this movie. But to help them decide which class they should take, they've got the guidance counselor on the 4th floor. So it's crazy that we're turning these prediction technologies to this problem, and unfortunately, not for this problem. Okay, how much can algorithms improve decision making? Well, we have a way of answering this question. We know how to do these sort of marginal value MVPF calculations. How many of you have seen these MVPF calculations? So these are basically ways to calculate the value of a policy, the value of public policy. You basically take the benefit to society divided by the net cost of government. We can calculate this for the algorithms that we built. This is a typical MVPF calculation. So it kind of says this is for aging benefit. This is written by aging beneficiaries, but here's a bunch of MVPFs for 100 and something programs, 33 programs. And if we calculate it for algorithms, the 4 algorithms we calculate for all sit up here. And you'll notice they have infinite return. And only 19 of the programs studied by Henry and Sprung-Kaiser have infinite return. Why do they have infinite return? They have infinite return because remember we're doing benefit divided by cost. But the cost of these algorithms are negative. And you want to tell me why they're negative? Like why does the bail algorithm cost us $8? Yeah, you get rid of people. You get money back because now you're not spending on all those people in jail. So you actually make money for implementing this algorithm, and you get these social benefits. So that's important. So to conclude this whole bit, these are incredibly high return opportunities. Why are they so big? I'll just give you a couple of reasons why they're big. Because algorithms operate on margins that are good from an economics point of view. In an economics point of view, what we tend to do with most programs is if you look on the left, we tend to sort of move down the diminishing returns curve. Let's say we give more benefits. And so then you get that little triangle. Yeah, you increase quantity, you get that gain. Algorithms don't need to change quantity. They're changing the sorting of people. To whom should we jail? Which teacher we should hire? By sorting, they're just increasing efficiency. So without changing any expenditure, they're changing the efficiency of the expenditures we've already spent. And so their gains are inherently first order. The second reason, of course, is that algorithms are cheap. But the third reason, which is what I'm going to get into next in the talk, is this, which is an old slide from a long time ago. Whenever I have to give behavioral economics talks, and I needed to summarize behavioral economics in one slide, this is the slide I would use. It's probably my favorite slide because nothing perfectly illustrates that people are weird better than this. Okay, so hopefully I can see why it illustrates people are weird. And if you can't, I can't. Okay, so so now what I want to do is we talk about can algorithms improve decision making. Now I want to move to why can algorithms improve decision making. So to do this, I want to ask the question, why are judges doing so badly in this test? Now how do I normally go about answering this question? Here's what I do. I come up with a cool hypothesis and then I test it. And this is like what I would roughly do. I might say, oh, maybe judges are in a bad mood. Maybe it's all about mood. Maybe they have stereotypes or whatever. I come up with an idea. And once I have the idea, we have a ton of machinery for testing this idea. Like a lot of machinery. It's actually quite striking how good the machinery is that we built in science. But it's also striking that the machinery for this bit, the generation of hypotheses, I don't have any machinery for that. In fact, I think it's fair to say that in all the work we do, the way we test our hypotheses is meticulous, but the way we generate our hypotheses is in the shell. It's just something we've made up. That's just a bizarre asymmetry in science. But there's something inconsistent here. What is a good hypothesis? It's a pattern that you've noticed in the world, intuitively. But if I just told you judges are bad at pattern detection, they're bad at detecting who's at high risk and who's at low risk, why is the judge bad at pattern detection and needs an algorithm, but I'm good at pattern detection, I don't need it? So why can't supervised learning algorithms help me generate hypotheses? Now, I'm going to the second part of the talk. I'm going to ask myself, let's actually do that. Let's actually ask the algorithm, let's actually build an algorithm to help us generate hypotheses. How would we do that? When we were trying to predict risk, the camera was on the defendant, and we had an algorithm predict what would the defendant do. That was the source of risk. Would they flee or not? Now that we're trying to understand the judge, we're going to turn the camera from the defendant to the judge and say, let's predict what the judge will do. Once we predict what the judge will do, it gets kind of interesting. So I'm going to try and do a very crude estimate here to ask which factors predict the judge's decision. Okay? This is not the interesting part. This is the fun. Okay? So the sixth most important factor in predicting what a judge will do is whether the current charge is a gun crime. You have a lot of historical information and you know everything about the person. But if the current thing they're being charged with is a gun crime, plays a pretty big role. The fifth most is whether the current thing they're being charged with is a drug crime. The fourth is whether it's a felony. Third is whether it's a property crime. Second, so now you see a pattern is developing. So what current charge do you think I'm missing here in the first one? Anyone want to guess? Murder. That's a very good guess, right? In fact, these findings already are so striking that Cass Sunstein has a paper called Current Charge Bias. That based on these results, that judges overweight current charge. In fact, it's not murder. The number one predictive factor, and it's almost misleading that I say this, because this factor is not just a number one predictive factor, it's extremely predictive, is the current charge of having the wrong face. So the mugshot is by far the most predictive factor in the printouts group. And to be clear, I don't mean some features in the mugshot that we coded up. I mean literally the pixels of the mugshot are the most predictive. And when I said it's misleading, here's what I mean. If I deleted every piece of my data set about the defendant, and I kept only the mugshot, so I get their arrest history, I get the current shot, I get rid of it all, and I just keep the mugshot, and I say, okay, now let's build an algorithm that uses just the mugshot to predict what the judge will do. That new algorithm, which doesn't know anything but the mugshot, explains about half of the variations the algorithm that has everything else. So this number one factor is about half of the signal, and then the rest is where the other bits live. So the mugshot's doing a lot of work, which is astonishing. It certainly wouldn't have been my number one hypothesis going in. But of course, part of what we have to do is we have to ensure that the algorithm is not just rediscovering something I already knew. So for example, what's an example of something in the mugshot that we might already know judges bias their decisions based on? Yeah. Race. Anything else? Gender. Yep. And in fact, gender plays a big role. Race, skin color, age, gender are all in the mugshot. So part of what we have to do is to make sure you found the mugshot matters, but this is why it matters. The second thing we have to do is we have to say, yeah, but psychologists have been studying mugshots for a long time. So we have to go and identify their factors. And they have a bunch of factors. In fact, they've identified 4 that are super important: trustworthiness, dominance, competence, fourth one is. Then we also want to make sure that it's not finding something that we know intuitively. So what we then did, we codify all these features in the mugshot. And then what we do is we have people look at the image and play a game where they have to guess, will this person be jailed or not? They're just going to make a guess. They don't have to tell us what the feature is. They're just going to make a guess, and they get paid for getting it right. And we've done it with people. We've also done it with public defenders' offices. So you get these incentivized guesses. So these are sort of human predictions. Here's an amazing, I found this amazing. If we code all of this in the mugshot, it turns out the algorithm rediscovers all of these. So that is, in the prediction from the pixels is all the signal you would get if you'd gone and coded this. There's no additional signal from these. But the converse is not true. Collectively, these explain very little of what the algorithm is found. Gender is the single most important one of what the algorithm is found, about 9% of what the algorithm finds. The remainder together are about 5%. So 14% of the variation is explained by the stuff we knew, which means 86% is stuff that we had no idea. So now, we have to ask the question, how are we going to find out when the algorithm was discovered so that I get a hypothesis back? To do that requires we go a little further. It requires that we build a way to communicate with the algorithm that is looking at pixels and making predictions. That's probably the meat of this paper. The way we do that is I'm going to show you how we built that procedure, then I'm going to show you what we do with that procedure, which is I'm going to give it to human subjects who use the procedure and generate the hypotheses for us. Okay? So here's the procedure. You've all now seen generative models. This is actually extremely reliable version of generative models, which are called GANs. They work especially well for cases. So we took all our mugshot data and we produced a mugshot GAN, which is an algorithm that produces synthetic mugshots. And so here, for example, are 2 synthetic mugshots and 2 real mugshots. And I don't know which are which, but I'm also pretty sure none of you can figure out which are which. It's actually quite hard. I have no idea. And so what we do then, given this mugshot, is we start with a synthetic mugshot. This is a made-up guy. We take the algorithm, apply it to the synthetic mugshot, and we say, change the mugshot, it's now moving in GAN space, to maximally increase probability of detention. And change the mugshot to maximally decrease probability of detention. That's going to give us these sort of endpoints of this picture. Left-hand side, highest detention, right-hand side, lowest detention probability. We're going to call that morphing. Then what we're going to do is we're going to take these morphs, take the end pairs, do a bunch of these, show these image pairs to people. This is another image pair from the endpoint. Show these image pairs to people, and they're going to play a little game. They're going to guess which of these pairs has a higher predicted release. They're going to be given feedback and a chance to learn, and then they're going to be given incentives. And so they get and have a chance to learn. At the end of all of it, they get pretty good at the game. And so then we say, hey, what do you think you were using to make these guesses that you seem to be pretty good about? So what we've done is we've created a communication channel where the algorithm can't really communicate its code, but it can give us these endpoints. And as humans, we can try to look at them and guess what we think we're seeing, which is what these people are doing. And now the question is there enough commonality in what people are seeing so that there's something common communicating through this channel? So, in fact, there it is. This is, for the first run of this is a word cloud of what people say. You can probably start to see some words pop out of here. And if you tokenize these words, it turns out that about 40% of the subjects in this experiment say, oh, I know what the algorithm is seeing. It's seeing well-groomed. And that's kind of interesting, because we can do more where this is coming from. We can now orthogonalize these images with respect to well-groomed, and do everything I just did again. Do that, now you actually get an even stronger pair. This one you can see in almost any pair of photos. Like this is a pair, this is a random shot. These are two ends of the spectrum. It's a synthetic. And this is probably, you can probably see what the second one come up with is. What they come up with is full-faced, fat-faced. Can't really write fat-faced in a paper, but it's basically fat-faced. Anyone want to guess? Well-groomed, you all surely know what it was. Well-groomed means more likely to be released. But how many people think heavy-faced is more likely to be released? How many people think heavy-faced is more likely to be jailed? Yeah, it's almost always about half-half. But isn't it funny? This is very strong in the data, so strong, it's the second feature that comes out. In fact, if you go and codify it, it's actually more impactful than well-groomed. Well, we can't even guess what sign it is, collectively. So, did these actually predict judge behavior? Yes, and by large magnitude. If we take the photos and we predict what judges do, without the algorithm, we just code well-groomed. It turns out, well-groomed people are much more likely to be released. This is the left-hand side of this graph. So much so, that it's about 28.7% more likely to be detained if you're not well-groomed. Does full face matter? Absolutely. Now you see the direction. You should be shaving, getting clean cut, and eating a lot. In fact, having a heavy face really does increase release rates. Also by huge magnitudes. Somebody mentioned murder. These are about half the effect of having committed a very serious crime. These are not small magnitudes. These are ginormous magnitudes. They are much bigger than the race effect to calculate. Much bigger. And much bigger than skin color. Skin color is much more important than race. It's a strong bias, social bias. So, do these predict judge behavior at huge magnitudes? Are these new? Yeah, if you actually go to experiments with public defenders and you ask them to make guesses, they basically never name these things. Yeah?
Do you have an explanation why they predicted so well if we can't make out which direction it goes?
Why the,
Like the full face.
oh, you mean the subjects in the experiment? Because I told you guys full face, but they were actually given feedback as to, here are two pictures, which is more likely to be released, and they were told which one was more likely to be released. So they were actually given feedback on the judge released this one or not this one. Does that make sense? And so they're getting feedback on that. So, are these new? Well, public defenders don't really name these features. It certainly was news to them when we talked to them. They even seem to work causally in lab experiments. So if you actually just run a lab experiment where you ask people, should this person be jailed, and you give them a little mugshot with tons of background information, and then for some people you synthetically make the mugshot more full-faced, people are like, oh yeah, that person should be released. So it suggests that there's actually plausibly causal. But this is not a paper about well-groomed, or a paper about full-faced. It's not even a paper about judgments. It's not even a paper about faces. It's really a paper about how to study people. Much like the first paper was a different kind of policy problem. It suggests one reason behavioral economics needs AI, close the first part of the talk, is that algorithms can help us tackle social problems. Which is, the point is, many of our problems are prediction problems, and we as humans are not great at prediction. algorithms can also help us understand people if we use them as predictive technologies for human behavior and then use that to generate policies. So that's one direction. And I think this is a totally, to me, this is probably one of the most important directions that will probably change the way all of science is done. Because I don't think there's any reason we should be doing science in the 21st century the way we did in the 20th or the 19th or the 17th. So now let me move to the second part, why AI needs behavioral economics. So to do this, I'll go through this paper we have. This is Facebook. Since you guys are young, Facebook is like TikTok for photos. It's still around. You can go on the website. It works. A website is something you visit on a browser rather than an app. Anyway, I can explain that to you guys. It'll take forever. So here's what we did on Facebook. We did a little experiment, an audit study, where we had people browse their newsfeed. And what we said was, we asked them how much did they like the post they saw. They answered for each post how much they liked. And we tracked details of the post. So let me show you what we found. On the x-axis, we have how much they liked the post, right? On the right-hand scale, like. On the y-axis, we saw where it was ranked, okay? So it's mean rank above median, so higher up, higher rank. So good news, if you like a post more, it's ranked higher, which means a near $1 trillion company knows how to build a recommender system. That's the good news. You'd be surprised if this were true. Here's the weird news. What we did was we actually tracked one more thing. Who was the post by? Like, what was their gender, or more importantly, what was their race? And what we asked was, conditional on how much you actually liked the post, this is your self-reported liking, did it matter who made the post? It turned out it did. Facebook systematically ranked posts by people of your own race, friends of your own race, significantly higher than posts of people from races and outgroups versus in-groups. Just to be clear what I'm not saying here. I'm not saying here people like posts by people like them. I'm saying conditional on how much they like the posts, Facebook hid the posts of their friends who are not of the same race. That's really weird. Well, so it gets a little weirder because we also audited the second algorithm, people you may know. This is an algorithm. Newsfeed ranks your posts, people you may know ranks potential friends. Did the exact same thing. Scroll through, tell us the people you may know, blah, blah, blah. X-axis, same thing, Y-axis, same thing. I'm going to do exactly the same thing before. As before, people you may know, if you're more likely to want to know that person, you rank higher. But now there's absolutely no in-group, out-group gap. Same company. And if any model you had about why there's racial bias, I think you would have expected there to be more bias in making friends than amongst the people you've already made friends with. Maybe you think there's no difference, but here I'm finding a huge difference. So then we went to India and redid the whole thing, not for race, but for religion, for between Muslims and Hindus. And what we found is the exact same pattern. In India, Hindus have their Muslim friends posts hidden, and Muslims have their Hindu friends posts hidden. But in terms of suggesting friends, Facebook is very egalitarian. It's like, oh, Hindus should meet Muslims at whatever race they're at. This is very weird. So what's going on here? So why is the algorithm biased? Why is it biased in newsfeed but not in people you may know? And as I said, existing explanations don't really give you an answer. Now, I'm going to give you a caveat. I can't give you a definitive answer without working for Facebook, but let me give you a hypothesis. And to give you this hypothesis, I want to tell you a story. I went to a friend of mine's house like several years ago. Very nice friend. She and I were going to hang out in the afternoon, and it was like between meals. And so, because she's a very nice friend and polite, she was like being considerate, and she put out something for me to eat. In fact, she put out Doritos. Now, maybe she knew this, but I really like Doritos. But she's very considerate. So she put out more Doritos. I really like Doritos. She's very considerate. You see where this is headed. At the end of all of that, I have to say, she was very considerate. I walked away thinking, what a nice person. I'm definitely never going back. Now what happened? Arguably, what went wrong, well, let's get one thing out of the way. I went wrong. I clearly have a problem with this. But in a blame the victim type situation, let me also argue she went wrong. How did she go? Well, her heart was clearly in the right place. She's like, oh, I want to give Sendhil what he wants. But she didn't give me what she wants, did she? She gave me what I ate. But what I ate is not necessarily what I want. Her mistake is the most basic mistake that anybody can make if you know a little bit of psychology. Choices are not equal to preferences. If you cannot find immediately a circumstance where you consistently make choices that are inconsistent with your preferences, there are one of two things that are true. You either don't know yourself or you're a sociopath. So her mistake is choice equal preferences. It's a well understood fact. It happens here because of self-control, want to connect conflict, but it can happen for many other reasons. But it's a widely ignored behavioral science fact. You know where it's most ignored today? In building algorithms. In fact, you can see how we can explain choices not equal to preferences. We can use it to explain this. The first part is, one of the most important aspects of the Facebook algorithm is it's not trained on my preferences. That's the x-axis here. Facebook doesn't know my preferences. We know it in our study, but how can Facebook know my preferences? What does Facebook know about me? What does any social media algorithm know about me? They do not know my preferences. They know my behavior. They know my clicks, they know my dwell times, but clicks don't need to reflect preferences. One way that we know choices don't equal preferences is, this is actually my favorite psychology cartoon of all time. You guys take a walk together, but it's fantastic. One way is something called in-group bias. The way in-group bias works is that my behavior favors in-groups more in behavior than in preference. So how much ever you may have no in-group favoritism in your preferences, I promise you, you all have a little bit of in-group favoritism in behavior. And it can be very subtle behavior. Like it can be in length of eye contact, how much you smile. It's very hard to keep in-group bias out. So if an algorithm is trained on my behaviors, it'll produce more in-group behavior, just like my friend. It'll give more, just like my friend gave me more videos than I wanted, this will give me more in-group than I wanted. But how does this explain people you've made over to the newsfeed? Well, this structure, this bias has very clear-cut structure. It appears when we behave automatically. It's more likely to appear when I'm not thinking much, when I'm acting quickly, when the consequences are low. I hope you see this is all social media. And if I said to you, which of these two contexts is low deliberation, quick choice, low consequence, when I'm scrolling past the post or when I'm choosing a friend, you can see what it is. So you can see mechanically more in-group favoritism, less in-group favoritism. More automatic behaviors, less automatic behaviors, and bias, non-bias. So weirdly, in the construction of this massive algorithm, what they've left out is a very basic behavioral science fact. And how do we know this to be true? How would we test this? Well, we can actually recreate a lab study that exactly simulates scrolling, puts people into two conditions, one which where they're more automatic and one which they're less automatic. So there's deliberate behavior, people you may know, automatic behavior, newsfeed. How do we do this? We give them more or less time pressure. Now we get choices, in this case, movies recommended by people, and we just manipulate the race of the recommender. And then we say, let's train an algorithm in each of these worlds. Because people are randomly assigned, their preferences are exactly the same. I'm just going to train an algorithm in these two worlds, and here's what we find. If trained on deliberate behavior with no time pressure, there's very little bias of what the movies the algorithm recommends. Train it in the faster time pressure thing, and suddenly you see massive bias, much like people using movies. So to summarize, the broader lesson here, the ML approach uses easy to predict behavior and uses predictions to drive decisions. That's what every algorithm built at scale involving human behavior does. That's what a recommender system is. And this has a naive presumption that measured behavior reveals preferences, objective humans. Now this problem transcends social media. It's not just recommender systems. Hiring algorithms, where you say, let me use the people that a person screening the resume tends to pick to train an algorithm. How much time are people spend screening these resumes? What a weird automatic behavior to hear. Pricing algorithms, you can just keep going. But it's not just those type of situations. Let me tell you a hilarious situation that not even audience launch of conflict. How many of you here know anything about baseball? Okay, a little bit. I'm sorry, I really dislike baseball. So for those of you who don't know anything about baseball, stay that way. It's an awful sport. Yeah. My ex-wife said it was men in pajamas, which felt right. I didn't understand why they put pajamas while playing an adult sport. Anyway, so this is called the strike zone. So while they're standing there in their pajamas swinging, the ball has to go into this little zone here. Okay. And if it goes there, it's called a strike zone. All that side is called the ball. Except for the thing. We actually have tons of data of where things go and what they're called by umpire. Imagine you didn't know what strike zone was. You could try to use that data to learn what the strike zone is, right? And what you find is this is the strike zone. You exactly learn this weird mass that looks nothing like that. It's not about automaticity or one-trick conflict. This is just human bias in your decision. But of course, it's also a pretty contrived example. Where on earth would we ever actually use data by some expert looking at something and making decisions to automate something? Certainly we wouldn't do it in baseball. We certainly wouldn't do it in anything more consequential and release it into the world as part of medical decision. No, that's actually exactly what we do when we automate everything a radiologist says. We literally say, here's this radiologist looking at their 250th x-ray. I'm sure that's a good judgment. Let's just go to 10. That is literally the pipeline that you use when you automate these things. And so the ML approach is quite problematic because it is missing the model that takes behavior back to the thing you care about. We don't want to automate what radiologists say. We want to automate their best judgment. So what we need to do is we need to use known psychology to model behavior as it relates to the user's mind and incorporate these behavioral insights into how we build machine learning. So let me zoom back a little bit and say, from this, I hope you can see there's sort of two inequalities. The first part of the talk was that, the second part of the talk was that in some sense, humans understand stuff that algorithms don't. They're trapped inside the data frame. All they see is the data they have. We understand the meaning behind that data. For example, oh, I see. When people make quick decisions, it doesn't mean as much about preferences when people make fast decisions. That's the sense in which humans have a lot to offer. This, in particular, behavioral science, has a lot to offer. Yeah. But the flip side is also true. Algorithms inside the data they are trapped in can see things that we never could. That's why this algorithm beat the judge in making predictions. That's why this algorithm, looking at data that I had access to, came up with better hypotheses about what judges would do than I could. So we're in kind of an interesting scenario. Both algorithms and humans have different advantages. And in fact, the disciplines, if you zoom back, have these complementarities. Behavioral economics understands the meaning behind human data. Computer science has very good tools for extracting signal in that data that we do not have. So arguably, there's a new discipline that integrates these two. But I actually think it's good to merge these two things together. Because what I hope you've taken away is that the merging of these two disciplines actually allows us to have new interventions. That's what the first part of the talk was about. Allows us to give us new tools of discovery. And I think that will create a virtuous feedback. So let me stop there, and if there are times, you can really ask me anything you want about this, anything else, classes, whatever you want.
You talked about using, I'm just quoting specifically, but let's say you talked about using algorithms in the judge's role, and you talked about maybe using algorithms for advising students, but what would you say about using algorithms to find the right judge, using algorithms to find the right student advisor? Because we talked about the interplay behind, humans having this human understanding. Like, I don't know about others, but if I was arrested for something, I wouldn't want a screen with either a green check mark or like a red cross deciding what's going to happen to me. So what do you think about this? So we choose the right judge with it, and then they use their own human,
Yeah, and to be clear, I 100% agree, and I would go even further. I'd say, I don't want to imply from the judge thing that we're going to automate a way to judge. What I want to imply is that the algorithm has found a signal which the judge doesn't. How we take advantage of that signal is going to be one of the more exciting things in the next 10 years. You give one example. I'll give you another example. Maybe all of these tools are never put out as anything but aids where the judge can look at their own past decisions and understand where they screwed up. I mean, quarterbacks get access to tape that they can study. Why shouldn't the judge get access to tape that they can study? I mean, I think the design space of using this information is enormous, and I think creativity is just going to be part of it. Yeah.
Can you elaborate on how the algorithm was implemented in New York?
Yeah, so the algorithm was implemented in New York by basically, once you deal with the issues and make sure that you have racial parity, it was implemented as a decision aid, where the judge was being given a risk score, and people were put into the risk bin, and the judge was told, this is the risk of this person, and there was a little bit of for what, which characteristics the algorithm relied on, basically. And so the judge decides, but the judge is basically given this risk score. And so, in some places, such decision aids have done badly, because I think because they were badly designed, but one reason we find them do badly is because the judge will listen when it matches what they want, but won't listen when it won't. So there are issues like that. In New York, that didn't seem to have happened. It seemed to have had about the effect you were hoping for.
Yeah, so a few years ago, there was like a paper that you wrote that was making the rounds about how these like huge healthcare systems were using this like biased algorithm that basically said you should provide care to like black patients who are like sicker on average compared to white patients because they were using to train the algorithm how much money you spent like caring for a black versus white patient. There's obviously disparities there, right? And so, my question kind of comes around like there's a lot of people in this room that are probably going to be involved in creating algorithms in the future and finding whether it's something to get into. So I'm curious what sort of concrete steps are like people like us should take into consideration when we're building these algorithms and how we can actually ensure that stuff like this doesn't already happen yet.
Yeah, it's a great question. Yeah, I think one of the things that we do in this class we teach around this, one of the things we do is we talk about the fact that most ML classes, the reason these algorithms are very poorly built is most machine learning classes. In fact, it's actually quite hilarious. Most statistics classes, econometrics classes, they all start with the data frame, and then they tell you what to do with that data frame, build the things or whatever. Most problems, in fact every problem that I know of, is not about something someone did down here. It's a mismatch between the data frame and the problem that you're trying to solve. And so the skill to develop is to know what are the common mismatches between problem and data frame, and then be able to articulate the problem, actually know what's in your data, and look at it. Even the Facebook thing is a mismatch. What's the problem you're trying to solve? I want to give people post a like. What's the data frame? Post a clicked on, or even worse, the dwell time of posts. Then you can ask, does clicks and dwell time equal preference? What's the mismatch? So that's an example of label bias. So there's kind of 4 problems that fall here. Label bias is one of them. Distribution shift is another. But it's actually quite analytical at this point, and you can actually just run through the 4 horsemen. And I don't know if I can find that out, but pretty analytical at this point. Yeah.
In the example you gave with the radiologist, you said that like you don't want to replicate what the radiologist does, you want to replicate what they should do. How do you even do that if the radiologist is the one labeling your data?
Great question. What you have to do is, again, you can't sit at the label level. So what you have to say is, labels are not judgments. They're judgments plus what happens when you go from judgment to label. A lot of error can creep in. So you have to model that error. So what are some things that happen? So fatigue is an example. Let's take that one. There's a bunch of others, but take fatigue as an example. The minute you know this, now when you're building an ML algorithm, you're like, oh wait, I'm missing a variable. Was this the first one they read or the 100th one they read? Makes such a big difference, doesn't it? But they didn't have that data. Because they're not even thinking about this variable. And so if you knew that variable, here's one thing you could do. You would ask the question, is this the kind, what would be my predicted label if it was seen in the 100th position? What would be my predicted label if it was seen in the first position? When you see big differences there, you know you have a problem, but there are some things that are so fatigue insensitive, so now you're able to get a standard error, so to speak, using this. But you can go further. You don't just have to use fatigue. We have stuff we're building that uses inattention which is the fact that certain types of things you're looking over here you may not notice over here. So you could put more and more structural models between judgment, whatever. And what you do is these turn prediction problems into what we call, or physicists and people in other fields call inversion problems. Where I'm trying to go from the label and I'm trying to invert back to judgment using judgment models. But it's roughly. Yeah.
I think you talked about that that the model should be trained on the best outcomes. It's easy. I think it's easier if the outcome is not really delayed. But what about outcomes that are really delayed, like over many years, even decades?
Yeah, so there are problems for which these algorithms are just not suitable. Like those are ones, like the labels we have just don't come around for a while. But even for problems for which we feel we don't have outcomes, go back to Facebook. See, they've got dwell time. You guys know dwell time? It's just like how much time do I spend like I send them. They got a lot of that. They have a little bit fewer clicks. They have a little bit fewer comments. You know what they actually want? I think most people don't realize this. Most people are like, oh, this is obviously what they're optimizing. They're not optimizing. They don't really give a shit what you do post by post. They're optimizing long-term engagement because you're an asset to them, and it's the NPV of ad revenue from you that they care about. So they care about long-term engagement. But long-term engagement has the problem that you're describing. That's like a data they can get very rarely. This they can get very quickly. But even with just this, because you know automaticity is going down, you're more automatic here than here. You can actually use that information to actually understand which posts are preying on authenticity and which are not. Because this slope is telling you the posts that are very, it's like the order thing. The posts that do much better on dwell time than do on commenting are the ones that are preying on authenticity. The posts that do equally well on all of them are the posts that do actually well. So you can actually build prediction problems to understand which ones are. So that's kind of, there's clever tricks here once you start doing it. And you can see, the AI space often feels like it's about like building transformer architectures, but that stuff is largely commoditized, and being able to add things like this is a non-commoditized process. Yeah.
I just wanted to follow up on like Facebook algorithms and more social media. So, I think obviously as you pointed out, there's like these inherent like problems to this new speed. So you get, for example, like Facebook feed. Is there ways to make it more like that's how, or is it more about like TV speed and like follow subscribers and is there like a way to like?
I think there definitely is, and I think the way to think about it is, we use racial bias, and misinformation is another good example. You get into a lot of random little fights, or little things that you're like, why did I engage in that? And I think this fact that we have often a variety of behavioral signals that vary the extent to which they communicate our true preferences is a way we can use the existing data frames to add it. So that we can actually ask ourselves which tweets or posts are as appealing to the high frequency data as to the low frequency data, and which parts of the space of posts seem to prey just on this. It's almost like saying a long time ago, before you guys were even born, people started to realize you gotta get rid of clickbait. So they started to create clickbait detectors. This is kind of an extension of clickbait detectors. It's saying what are the things that are preying to the more automatic things and not to the other. And I think that's probably the most straightforward way. And this is
Thanks so much, Professor. I was just wondering, based on your presentation, it seems that a lot of the impact that both behavioral economics and AI can drive happens through collaboration with like businesses, like through Facebook, and government agencies like the sentencing decision. And I just wondered, in terms of your future model of academia, do you see that collaboration happening a lot more frequently? And what sort of prevents such collaboration happening? And I'd love to hear more about your experience like navigating those sorts of relationships.
Yeah, it's a good point. I think, and then you were saying there's something that you guys are cultivating. I think we're going to see more and more of that. And I'll tell you why we're going to see more and more of